Have you ever wondered how stuff actually moves and interacts with other stuff? You've always heard about things like force, velocity, acceleration, but how does all of that get transferred between one thing to another? What actually drives all this motion? That's what you're going to figure out today in the full guide to momentum. So, I really hope you enjoy this, and let's move on to the first topic. When Newton wrote his second law, we all know it as F is equal to ma. But what Newton actually said was that a change in motion was proportional to the force impressed on it. Now, this sounds pretty complicated. What is a change in motion? What does force impressed on it mean? Well, we can define all of this. What Newton meant by impressed on it just means what force was put on it or what force was exerted on it. So impressed is just another word for exerted. But what about this change in motion? Well, this was momentum. So what Newton is really trying to say in his second law is that momentum is proportional to force. So now we know what momentum is, what force is. Well, we know what force is, but now we know what Newton really meant by second law and what momentum means to him. But what is momentum in terms of other stuff? We know it's proportional to force, but we don't know anything else. So there we go on to the next major aspect of momentum, what it is in terms of other quantities. Momentum, which is represented by P, is equal to mass times velocity. And now this makes sense. Mass times velocity is proportional to mass times acceleration, because mass times acceleration times time is equal to mass times velocity, and that's basically exactly what it is, as time is that constant that is the proportionality constant. So there you go. This is what momentum actually is in terms of other stuff. Let's talk about first momentum in Newton's first law. Well, what is Newton's first law? Newton's first law is an object at rest. So if I have an object over here, it's gonna stay at rest unless I have an external force. Now, this means that as long as any force isn't applied, nothing's going to happen to the object. But let's reframe our reference. If it stays at rest, that means the velocity is equal to 0. And what is momentum? Mass times velocity. So this means the momentum is 0 for a closed system. And that's how momentum connects to the first law. Anything in a closed system, the total sum of all momentums will be 0 unless there's an external force which causes motion in that system. Then that momentum will be the force times time. So that is the first law, how momentum directly relates. But that's not the only thing we can tell from momentum being in the first law. What if that object is moving? Because that's the second part of this law. If an object is moving, it stays moving until something changes it. And that means that since it has constant velocity, momentum is constant. And that means, and since that's there, it doesn't matter how much force it does matter how much force. What am I saying? It doesn't matter what the velocity is. The momentum only changes if the velocity changes. As long as the velocity stays constant, the momentum stays constant. So this is in reality a slightly more general term, and this helps us realize one main point. Momentum is constant in a closed system. Well, that's one law. What about the other two? Over here, I have Newton's second law. Newton's second law is, of course, the very famous force is equal to mass times acceleration. Now, in my intro to momentum video, I discussed talking about how momentum is the actual original statement of the law, so I'm not going to spend too much time. Instead, you should go watch that video, and when you come back to this video, or you can finish watching this video, I can show you some new connections that arise from momentum's second law, and Newton's second law and momentum. So, basically, let's look at what Newton's first law originally said. Force is proportional to momentum. But that means if force changes, then momentum changes. But we know that we can always alter the amount of force we have on the object. So what does this tell us? This means that force is the one that changes momentum. And that's what's insanely important. They're not just related. One directly changes the other. So now we know the force changes the momentum. This also creates the foundation for something else. Impulse. Now, since force changes momentum and we showed that momentum is force times time, that means we can have delta P is equal to force times the change in time. And this delta P quantity is impulse. So in reality, Newton's second law is what causes the quantity as impulse to be defined and what tells us that force is the one that changes momentum and force is the one that does the action, as that's why some textbooks sometimes refer to force as action, and that now proves how the cause and effect relationship of these two quantities. So that's 2 out of our 3 laws covered. Let's now cover the third law. Alright, let's start by saying, what does Newton's third law say? Well, it says that for every action, there's an equal and opposite reaction. So the force of object 1 and object 2 is equal and opposite to the force of object 2 on 1. Now, let's combine this with our other laws. Since force changes momentum, this means that there will be equal and opposite changes in momentum. And do you know what happens to equal and opposite changes in momentum or in any quantity and they add up? Well, that becomes 0. And that is exactly what is the biggest reason why all of this happens. Because the third law proves that initial momentum is equal to final momentum, and which is basically conservation of momentum. Now, if you're a little confused on the terms conservation of momentum, impulse, and other stuff, I will be making more videos about these different quantities, but what I do want you to know first is that these quantities all come from Newton's three laws. But what does the story paint in full? Well, this basically shows that the fundamental quantity of all motion is momentum, not force, not acceleration, not velocity. Momentum. And force is what changes it, and everything in this universe is governed by it being conserved. There are a few things that we all know. We know that momentum is equal to mass times velocity. We know it's also equal to force times time. From my last video, we were also talking about how Newton's second law really is that force is a Force is a change in moment, or no, not force. Force causes a change in momentum. But what would that change represent? Change represent? Well, that would be impulse. Impulse, which is often denoted as J, is equal to the change in momentum, or it's force times change in time, or it's also equal to mass times change in velocity. So that's pretty much it, and that's what impulse actually is. But the biggest thing is that instead of just being like a change in momentum, it represents basically all the action done by forces. If you remember in my last video about Newton's laws and their connection to momentum, we talked about how in Newton's second law, again, force is change in momentum, but the third law, we're talking about how everything has an equal and opposite force. Every action has an equal and opposite reaction. And basically, instead of saying equal and opposite reaction, in this case, we could say equal and opposite impulse. This over here is also a very valid definition of Newton's third law. Another very, very powerful application of impulse is how it can predict many different scenarios. So let's run through a few of them. Let's say I'm trying to catch a ball. Now let's draw a diagram over here. We have a ball that's coming to us over here that's trying to catch it. Now, there are two main ways we could approach this. Either keep our hand in front of us and rigid. So basically, there will be a very, very low amount of time, but since it's the same momentum, the ball has the same mass and the same speed, the force is going to be maximized. That's why it hurts. Or we could kind of catch with the ball or give in to the ball. As what we'd be doing then is we would be observing the force kind of, but instead of absorbing the force as we normally say, we would just be spreading that same amount of force over a larger interval of time, thus still canceling out that momentum and energy. Now, there are many, many different examples, but this is just a very good example which explains momentum's, or really impulse's, connection to force. The biggest takeaway, though, that I want people to know is that momentum is kind of like impulse is kind of like the dose of force. How much of it over how much time, and that is really what predicts all of motion instead of just the force that applies on it. This is very, very similar to conservation of energy, as a conservation of something basically just means that the initial momentum, Pi, is equal to the final momentum, or that the net change in momentum is zero in a closed system. Now, what is momentum? Well, momentum is mass times velocity. So, mv1 is equal to mv1 plus m1v1 plus m2v2 and so on is equal to m1v1 prime and so on and so on. Now, this system will come in very, very handy in a later thing where we talk about collisions. But the biggest thing for now is that what we're going to do is we're going to examine what happens when we have these different terms, these different velocities. How can we tell what the final velocity is? Now, today we're going to be now that is pretty much the entire focus of collisions. But today we will not be covering collisions. So what are we going to do? What's going to happen normally is we're going to have an initial object at rest. Now, this means that one of our sides is going to be equal to 0. And then this will also equal the final momentum. But you can't have two positive velocities. So what we're going to have one positive and one negative velocity. Or one positive momentum and one negative momentum. And again, what this does is this reinforces the idea that momentum is a vector. It is not a scalar like energy. That's also what makes it different. It is a vector. Now, though we know momentum is a vector, we know that the final or an initial momentum can both equal 0 while their individual components also have momentum. And that's a very, very interesting consequence. And it's actually what helps rockets go into space along with many other things. So let's move on to an example. Over here we have our first problem. Now I did say that that we would mostly be covering problems that would have zero initial momentum, but the reason I'm covering this problem is it also teaches another very important lesson. So let's solve it. A 4-kilogram artillery shell is moving forwards at a speed of 120 meters per second when it explodes into 2 fragments. One of the fragments is 1 kilogram and moves forward at 300 meters per second. What is the velocity of the 3-kilogram fragment? Now, since it's conservation of momentum, most of you will immediately start thinking of momentum. But if I just presented this problem, some people might be like, ooh, nice. It explodes, so maybe, and then we have our mass and velocity, so maybe we could use conservation of energy. But we don't know with how much energy it explodes, or what the potential energy is, or any of that. So it's not enough information to solve it by using conservation of energy. So what are we going to do? We're going to use what the title of this video says, conservation of momentum. Well, what's our initial momentum? 4 kilograms times 120. Now, our final momentum is a 1 kilogram moving at 300 meters per second times a 3 kilogram moving at some velocity v2. Now solving, we get 480 is equal to 300 plus 3 times v2. Then we get 180 is equal to 3 times v2, or v2 is equal to 60 meters per second. Now, that is the answer to this problem, and as you can see, it's pretty simple. But if we would have tried to use conservation of energy or forces, it would be a complete nightmare to solve. And that's what makes this so useful. It can make stuff that would normally seem really complicated really easy, just like conservation of energy. Because the universe is kind of like bookkeeping this. Okay, since everything has to remain constant, this is how it must work. But the universe doesn't really bookkeep forces. It bookkeeps energy and momentum. So using forces normally becomes so much harder. So that's our first example. Let's move on to our second. Example 2. A 2,000 kilogram rocket, including fuels, is stationary in deep space. So that means there are no external forces. It ejects 500 kilograms of fuel at a speed of 1,200 meters per second. What is the velocity of the rocket after the burn? Well, again, let's start by using conservation of momentum. Well, we know that it's stationary, so 2,000 kilograms times 0, which is 0, which is one of the main problem types we talked about when we were first talking about momentum. Now this is equal to 500 times negative 1,200. The reason I'm saying negative 1,200 is because it's ejecting the fuel, and when you eject the fuel, it goes backwards in comparison to the actual rocket moving. So that's why we're going to have that be backwards and negative, just to show once again that momentum is a vector. Now, it asks us what's the velocity of the rocket after the burn. Now, we know the mass of the rest of the stuff would be 1500, and we have our V2. So 500 times 1200, so 60 followed by 4 zeros, or 600,000, is equal to 1500 V2. Now, dividing everything, we get V2 is equal to 400 meters per second, forwards, not backwards. And now, again, at first glance, this seems very confusing. How do I have something that starts stationary and then you have two things moving? But remember, they're moving in opposite directions, and since momentum is a vector, again, the final momentum is still 0. It's just that momentum got split into a positive and negative component. So, there are 3 types of collisions. Type number 1, elastic collisions. Type number 2, partially inelastic collisions. And type number 3, perfectly inelastic collisions. Now, each of these have different formulas when it comes to calculating momentum before and after. So, let's cover those formulas. But before we cover those formulas, let's understand more about these different types of collisions. Now, remember, by conservation of momentum, in all three, momentum is conserved. What varies, though, is kinetic energy. In elastic collisions, kinetic energy is conserved. In partially inelastic collisions, kinetic energy is lost. Could be other things due to heat or something, but this is what a lot of collisions will happen, partially inelastic or perfectly inelastic. But with perfectly inelastic, you will have the maximum amount of kinetic energy that's lost while conserving momentum. Basically, it's losing as much kinetic energy as possible without violating the laws of physics. So, those are the couple different characteristics of these collisions. Now, let's talk about formulas to calculate momentum and velocity before and after. Now, elastic collisions is just the standard conservation of momentum, where you just have the very simple law over here. For perfectly inelastic collisions, the maximum amount of kinetic energy lost while conserving momentum actually comes when the two objects stick together. So you'll have your m1v1 plus your m2v2, but then since the two objects are going to stick together, we're going to have these two over here, the masses combine, and then just have one final velocity. Now, you might have noticed that I skipped the partially inelastic collisions. Well, that's because the formula is very complicated and more advanced. Now, for those of you who want to look into it, you can search up something called the coefficient of restitution. Now, this coefficient of restitution kind of determines how much kinetic energy is lost. Now, if you look at those formulas, you'll realize that if this coefficient is equal to 1, it just condenses to perfectly elastic. And if it's equal to 0, if it's equal to 0, it'll be perfectly inelastic. And the symbol is E. So if E is equal to 1, elastic, 0 is less than E is less than 1, you have just inelastic or partially inelastic, and E is equal to 0 gets you perfectly inelastic. Now, over there, that is also one very, very important concept, the coefficient of restitution. Now, this is also very important for, let's say, because you can even apply the perfectly or some of these collisions
in reverse to understand the initial velocities of these two stuff. So that's really about it for this video. I will be covering more examples and stuff in my next couple videos. But besides that, thank you so much for watching. See you in the next one, and bye bye.